Hello and welcome to another lecture on debouncing. So we talked about debouncing when we are concerned with handling noise. Noise from the outside world. For example, a button being pushed. A button being pushed might look like a 1 and 0 to us, but is it really? A button being pushed actually looks something like this. It just goes, well, let's get a little more artistic here, but it looks relatively noisy. And the problem with this is it's not very digital, and so what we want to do is we want to make that digital. Let's actually take a look at an example here that I have lined up from a previous experiment that I like to use. Let's see, I'm going to open up an image here, open with Windows Photo Viewer, and what you'll see here is a, well, it was taken with a hand camera, but what we have is this, you see this, the blue line is the switch. It's basically very noisy. You see there's a lot of bouncing. Now if I was to just run this through a single flip-flop and just say, what does it look like? Let's see what noise actually gets filtered out when we use flip-flops. If you see here, the output of the flip-flop isn't quite as noisy as the input analog signal. Now this is not really comforting. We still see noise. We actually see metastability. We see our signal not actually achieve a full true or 1, and we also see it not achieve a full 0, and that's called metastability, where the signal isn't necessarily a 1 or a 0 due to our signal, our input analog signal, or input any kind of signal actually failing to stay stable during the setup and hold time of our flip-flop. So how can we fix this? Well, we talked about one approach, which is a debouncer. A debouncer says, okay, let's take the first time this signal is valid. Okay, let's take the first time this signal is valid, and let's actually just say that's it. We're gonna ignore all the other noise until the end of time, until this circuit, we know that it's going to stop wiggling around. So we define a period of time in which we say, I'm going to ignore all other inputs. And let's make this red so it's easier to see. So there we go. It's nice and visible now. Let's say we tracked it right here. Let's make it more interesting. Let's say that the first time it went valid was actually here. And let's just ignore some data here to make it a clearer picture. There we go. And so that's what we have to work with. And so we say, I want to only generate a single clock-wide pulse for this noise. I want to generate this, and I want to ignore all subsequent noise that occurs. Now, realistically, we know one flip-flop is not enough. We can see right there that some noise still gets through. We have noise on the front end, noise on the back end. And what you'll see here is if we look at the switch design, switch characteristics, they'll actually say that when you push a button, that button will actually have a bounce period, a noise period, and they'll characterize it. They'll tell you it's on the order of milliseconds or microseconds. And actually, careful board design or circuit design can also minimize some of this noise. What do I mean by that? Well, you can use pull up or pull down, which would actually bias the circuit such that it's always going to be a 1 until somebody gives it a strong enough ground. There's a strong enough ground contact. So there's other techniques. A debouncer is sort of an old school keyboard debouncing approach. It would, whenever you push a button on a keyboard, it would look something like this, but we don't want all that extra noise. We only want to see the one key press. So there's our problem. Okay. So let's get rid of this for now. We sort of have a dialogue that, and we agree that this model here, albeit very simplistic, it kind of represents what we're going for. It kind of it gives us a picture to work with. And so let's see, what is it? This will actually bounce around in some frequency. Let's say it's 5 milliseconds. So we want to take the first time it goes high and ignore a 5 millisecond pulse. And let's just really characterize this nicely. Let's leave it like that. Okay, so let's say we have a clock, and our clock runs at let's say 100 microseconds. Well, that means we're going to have how many? We're going to have 50 clocks. So very simple here. We have 50 clocks. Let's make 5, cut it 10 times, and scale accordingly. 2, 4. This is just to show you how our signal, our clock signal, lines up to an outside signal, an outside asynchronous noisy signal. Okay, let's see, did I get 5? I hope so. Okay, so we need 10 of these. So what we're going to do here, let's just copy, copy. So I think we're at 30. So now we're at 60. Fantastic. So we only wanted 50. So we'll just stretch this out. There we go. Okay. So let's think about this. This is our signal noise. And what we see here is that it could perhaps might actually meet the setup and hold. Let's just draw a line here and ask ourselves, would it meet setup and hold of this clock? Probably not, right? Probably not. So what about this clock? Maybe, I don't know. I mean, it's realistically, it'll probably meet the setup and hold here. And so what we can do is we can say, fine, we see our first valid clock cycle, our first valid pulse right here. Let's make that a different color just so we're not. So there we go. That's nice. Okay. And it's going to be a 1 clock high wide pulse. Well, how do we make that? Well, we can't, right? We can't just do it right off the bat. We need some logic here in between. And so let's determine, let's just kind of come up with an arbitrary guesstimate of how many times this clock will be high for what period. And it's going to start looking something like this. This is arbitrary, but it illustrates a point. And this is sort of our digital, almost our logic analyzer view of the analog signal we're playing with here. And I'm going to say it doesn't pass. And again, what makes this actually go from 0 to 1? What actually makes it so that it's high or low? Well, the idea here, And let's start labeling stuff, so we can just say clock and Q. And where Q, what do I mean by that? I mean that we have a flip-flop here that is taking our signal, our dirty signal, and it's outputting it right there. So so let's say that this is our data. Let's just scrunch this down so we can start having a more meaningful conversation. And we can see everything on the same line. Let's say that this is our D. And this is our Q. Okay. What actually decides whether or not it goes to a 1 or a 0? Well, every flip-flop, every flip-flop will have basically what you call a voltage input high and a voltage output high. They have regions that are defined that tell you when we'll accept it as an input as a 1 and when we'll output it as a 1. And so let's just define what those regions are. So for this example, I think I chose this to be our voltage input high. Very, very large window, right? Almost absurd. Actually, I think it, well, let's get really accurate here. And actually, with that said, that means that this probably should have stayed a 1 a little longer. So there we go. And then there's another region. Okay, so let's say we have a flip-flop that has voltage input high and voltage input low defined as such. So what does that mean? So what you'll see here is in any data sheet or any standard cell library, they have a output high. What is the output? What is the voltage output when there's a high? VIH is what do we call a 1? When is it high? When is it true? And that obviously will be less than our output because our signal can't always be a perfect 1 volt, 5 volt, or whatever the reference voltage is. So then we have voltage output low and voltage input low, right? And so these are actually what determine what values are actually captured and when. It's the design of the circuit that controls or decides when we decide it's a high or a low. For more on that, I would actually take a circuit design course. Yeah, I won't do it justice here. So what do we do here? If we just put one flip-flop there, that's nice. We might actually get rid of a lot of the noise. A standard approach here would actually be put 2 synchronizers, 2 flip-flops in a row. Reason behind this is that this signal is actually quite sporadic, and it might actually, we might have got a false setup or hold here. We might have actually got something that looked like this, and that might have caused us to go higher sooner, and we didn't want it to. Or perhaps this jump right below the voltage input high. And what you see are runt signals. You see noise that actually ends up on the other side of the flip-flop. And just to make sure you all know what I'm referring to, I'm going to open up the original example here. So what you see here, right, is the signal went high, And our flip-flop, the yellow signal, our input signal is blue, our yellow signal went high sporadically but didn't reach. These are runt signals, they're noise. We don't want that. So what I do to clear that up is I add a second flip-flop into the mix. And this is called a synchronizer. And what I do is I in essence actually just flip-flop the data we have already coming through. And what happens is those runt signals will probably, and it really just looks shifted. All it does is look shifted by 1 clock cycle. And what does that do? Well, the thing is, these runt signals will probably not meet the setup and hold time of the next flip-flop. So when noise gets through, these get filtered out. So the idea here is now we have a clean signal, but we really only want to have one version of, we want one flip-flop wide. Well, first things first is we created an edge detect. And so an edge detect allows us, and so what does our circuit look like right now? So we're going to say Q2, Q1. Let's start giving these more unique names. So our circuit starts to look like this. We have a signal D. Let's just call this dirty signal. Just that way it's more obvious what we're dealing with. And let's say that gets input into here. And we have our usual clock driving both. I'm not going to get too artistic here. I don't want to waste your time with practicing Visio in front of you. So now we got a synchronizer. This little block here, these two flip-flops back to back, this is referred to as a synchronizer. And what does it do? It just removes instantaneous noise that might have eked through the first flip-flop. It just gives you a clean signal. Some will argue you need more flip-flops. Some will argue you need no flip-flops. Well, actually, I haven't heard that one. But we use 2 in practice. You can use as many as you need for your situation. Just make sure that you don't put too many of these in line. Otherwise, you'll actually filter out the signal. Because if the chain of flip-flops is longer than your signal, meaning I have 50 of these, 50 flip-flops, and my noise is 5 milliseconds, there's a small chance I won't even see that signal get through. So if the signal is high for 5 milliseconds, meaning we want a constant 1. Okay, so back to the original statement here. I want an edge detect. So an edge detect gives me a clean way to delineate when a signal goes high immediately. And the way it works is it compares the current state of the flip-flop. That is an ugly AND gate. I apologize. It compares the current state. And what you want to compare is that currently 0? Have we not got a clean signal through yet? And if so, I want an output here. I want to generate a 1 if the first flip-flop has seen a 1. So let's say we get let's take an example here. Let's say we get a 1 here. So there's a 1. But it hasn't gotten through to a 0. It hasn't gotten through to the next flip-flop. We have a 1 on this side of the flip-flop, and maybe it's a 1 here. And we have a 0 here. What will happen is we'll generate a 1 because we're saying this is the first time I've seen 1 go high. What I'm doing is I'm saying I haven't seen it yet, but it's before us. So what would that look like? Well, that probably looks something like this. It's going to trigger on when this guy went high, and it's only going to go for one clock cycle, right? But if you look right here, this goes low again, so it's going to go high right here. And again, this isn't all perfectly to scale. I'm assuming that you'll forgive me. Just to understand, I have artistic limits here. But this here is the beginnings of a debouncer. It's the beginnings of a filter. We still need somebody to keep watch for any additional pulses and ignore them. Because you notice here that that went high again. If we were monitoring key presses and somebody pressed the letter K, we might actually see 2 key presses of K, which is incorrect. It's actually just noise from the button. And so what do we want to do? We actually now want to create a timer. A timer that says, the first one I see, I want you to ignore every subsequent pulse that might have happened. And I want you to do that for approximately 5 milliseconds. And so what we want to do is we want to create a timer. A timer block. Okay. And that timer block, what's going to happen is it's going to kick. It's going to kick once the first time you see it. And what you're going to say is, while the timer, and we'll create some artificial states for our timer. We'll say while the timer is counting. Let's just say, and it's a down counter. I'll say is counting. Whenever the timer's counting, we don't want to accept any inputs. So what we're going to do here is we're going to say while the timer is counting, and unfortunately you're going to get this. So you're going to say, okay, we're actually going to I'm going to reword that a little bit here. I'm going to say while the timer is not counting, meaning we are now beyond some 5 millisecond period. So what am I saying here? I'm saying our timer is going to count. It's going to be a 5 millisecond timer. And what's going to happen is it's going to have a start. We're going to have a start input to it, and it's going to tell us when to start counting. Okay. And once it reaches 5 milliseconds, it stops counting. Pretty simple design, nothing fancy here. What's going to happen is we only start counting. Wow, that is really a deformed AND gate. Sorry. We only start counting whenever the timer is not counting. So that means that we are now establishing the beginning of our 5 millisecond timeout period. And we're saying we're not going to accept any additional inputs. Okay, we're not going to accept any additional inputs. We're not going to have any additional edge detects until that 5 milliseconds is done. Okay. And we can do a handy dandy little edge detect to tell us right here to detect the first time that we start counting, and we can use that to say done. So let's take a look at, we're going to create a signal here to say clean signal. And it's just going to be a one pulse, one clock-wide pulse, right? And so we had a pretty simple thing here, right? So this thing is only going to trigger once, and our clean signal is going to actually happen just a little later. It's going to happen just right around here because start gets issued. And that is our design. That's relatively simple, right? Okay, well, thank you. I'll go over the Verilog for this a little later.